My name is Sergey Nikolenko, and I'm here to talk to you about synthetic data and generative models for deep learning, etc., etc. Yeah, thank you. Thank you. Does it work now? Yeah, now it does. Actually, usually, I want to, as usual, begin with a few. One, two. Does everybody hear this echo around here? Yes. Yeah. Is there any way to make it better? No, because I think in the first talk there was no echo. Okay, never mind. So I have been a speaker on each and every one of the AI Ukraines, starting from 5 years ago in Kharkiv, and since then. Okay, this is the first time in Kiev, so I'm very happy to be here, or at least nearby. And I want to begin by thanking everybody who has been organizing this conference for all these years, especially Sasha Konduforov. Thank you very much. I'm sure you're here. AI Ukraine is a very special conference for me personally, because this is not just a venue where everybody has always been happy to see me and everybody has always been inviting me for all these years, but this is also the venue where I met my current partners in crime, current partners in the Neuromation company, which we founded a couple of years ago, and we actually met with Kostya Goltsev 3 years ago, I think, at AI Ukraine, and we met with Max Prosolov 2 years ago at AI Ukraine. And Max is here also. He's not. No, of course, he's not come to my talk. That's expected. But I thank them, and I thank this wonderful opportunity to meet even more wonderful people here. And okay, so all this aside, I'm here today to talk to you about synthetic data and generative models in deep learning. And I have to basically. You know, they say it's in bad form to begin by apologizing, but I have to begin by apologizing because usually on all previous AI Ukraines, I delivered very packed talks where I had like 120 slides for 30 minutes, and each of the slides had 10 different formulas, and I had to explain 1% of the slides, etc., etc. Today will be a very different presentation. Today I will actually speak about a relatively simple idea, and I will show you why this idea is important. I will try to talk to you about how it is unfolding now as we speak, but actually the basic concept of applying synthetic data for machine learning and for deep learning specifically is really, really simple, and I hope I will drive this point through very quickly. Okay, so I'd like to begin with some motivation, and being a researcher, and I suppose that most of you here also are AI researchers of some kind, I am of course always very skeptical when business people come in and try to produce some sort of bullshit reports. But it does serve a purpose, as I found recently, and the purpose is these reports can serve as wonderful points of reference. So if you can find something, if you can find the problem you're working on as an open problem in a McKinsey report, that's great. And that really adds something to your slides usually. So let me begin with the McKinsey report, or actually a compilation of several AI state-of-the-industry reports that I read recently. And basically all of them agree that AI adoption and the adoption of deep learning, of computer vision, of generative models, of natural language processing, of everything that we see and discuss in conferences like this, the adoption and the drive to new domains of application for these new research advances is basically limited by data. So all of the reports, all of the research on this in this field agrees that the main limiting factor for discovering and driving AI to new domains of application is basically the data problem, right? So in many applications, you simply do not have the data and you cannot have the data. In some applications, you have the data, but it takes some prohibitive amount of time and money to produce, for example, labeled data. And in some applications, you have difficulty generalizing from the data you have to the data that you want to study, but you do not have. And finally, in some applications, you have data sets, but they are imbalanced and biased, right? So this is also an important problem where, for example, I don't know, imagine, I will not go into like racial bias or anything, but imagine, for example, an MNIST-like data set where you have only 10% of zeros. And I mean, the 10% of the zeros that were in the MNIST data set. So 1% of the data set is zeros and 99% are other digits. This is also a very common occurrence in practice. So what we do at Neuromation, and one of the main fields of our core internal research in Neuromation that we do is fighting all of these issues and overcoming all of these issues with the notion of synthetic data. So the main idea is extremely simple. Synthetic data is basically data which has been automatically produced, and since it has been automatically produced, I will explain in specific domains, especially in computer vision, but since it has been automatically produced, we know everything about this data, right? And since we know everything about this data and we control it perfectly, we are able to achieve all sorts of labeling which comes for free, right? So the prototypical example, and the example that I will be talking about throughout most of my talk, is computer vision, of course. And in computer vision, for example, you can imagine a 3D model. I will show some nice pictures later. So, by the way, in my presentation there will be a lot of pictures, and some of them will be relatively involved. So, if you have any difficulty seeing or anything, please come closer to the screens. So the prototypical example would be to consider, say, a 3D model scene, for example, a scene of this room, and in this room, all the objects would be represented by their corresponding 3D models, right? And then what you would do is, for example, you want to study the segmentation problem. I hope you all heard about the segmentation problem. Given a picture, given an image, find out which object each pixel in this image belongs to, right? So find out draw the silhouettes of each and every object and shade which specific object this instance, this silhouette belongs to. So how do you gather data for a segmentation problem? It's hard, right? So it's very easy to get pictures, right? You can Google billions of images. But it is very hard to label these images, right? So if you imagine human-produced, manually produced labelings of images like this, you actually need a live human being drawing the silhouettes and picking which specific class this silhouette belongs to, and it's hard, and even if you hire some wonderful people from Amazon Mechanical Turk, it's still hard, and now it's also expensive, right? So, and suppose now that on the other hand you have a synthetic scene where you are doing the rendering, so you know where the camera is, and the camera looks at objects that you have placed in this scene, and you know all the coordinates. So of course you know what every pixel belongs to. And of course you can do pixel-perfect segmentation labeling, for example, at no additional cost once you have this scene. And of course you can have millions of images of the same scene, or of slightly randomized things. So for example, once I have the model of a chair, I can place thousands of different chairs in different combinations. I can throw them in a pile, I can stick them to the ceiling, whatever. And all of this, again, will be perfectly labeled, right? And the problem, of course, is that images like this are just synthetic data, right? They are cartoons, basically. And the main adaptation problem would be to transfer the models that you have trained on synthetic data like this into real images, so that models trained on such cartoons would actually make sense on real images. But as we will see, people have been rather successfully coping with problems like this. Okay, so this is the basic idea of synthetic data, and of course the major example throughout my talk will be computer vision, so I will actually, I will just say maybe a few words about synthetic data in other domains. Okay, given that it is that simple, it is actually very surprising, and for me it was very surprising that synthetic data has been virtually unexplored before about 2015, 2016. So in deep learning, in computer vision, there have been some works on synthetic data, but they were few and far between, and basically they all dealt with self-driving cars in some way. Because for self-driving cars, it's especially especially understandable that first you need a huge data set. If, for example, you want to learn to navigate, and of course you need a huge data set if you want to learn to navigate from pictures, from cameras on a self-driving car. And on the other hand, it is also absolutely clear that there is no way to gather a real-world data set. Because in a data set for learning to drive, for example, there must be all sorts of emergencies. There must be all sorts of unpredictable situations that can occur, because these are the actual situations that, you know, this coverage is actually what determines the safety of your self-driving car ultimately. It has to learn, if you wanted to learn not to hit people, you have to have a data set where some people have been hit. And of course, it is really, really hard to collect the real-world data set of people being hit and run over by cars, and this will be even more expensive than Amazon Mechanical Turk, I'm afraid. So, for applications like this, it was clear all the time that some sort of synthetic data is inevitable, but again, the papers are very few. I really don't know the reason for this. So you can trace some mentions of synthetic data, some applications back to the 2000s, to the first decade of the century, but basically, I mean, this is the most, I think, involved work that I could find, and it's from 2010, and they use synthetic, as I explained, they use synthetic scenes to detect pedestrians on the streets, specifically for the purpose that I explained, for self-driving cars. And this picture here actually shows the prototypical pipeline of training with synthetic data. So you create a virtual world, then you create a training set, which is basically a virtual video sequence, then you train on this, you train the classifier, you train the object detection thing, and then model, and then you test it on real data. So this is very important. Of course, everything that you train on synthetic data will have 99% accuracy on synthetic data. The trick is, of course, to transfer back to real images. But around 2016, guys, can we do something with the echo? I really think there was no echo in the first talk. At least I didn't hear. So around 2016, interest suddenly spiked. And actually, I still posit that synthetic data is criminally underexplored in computer vision and in machine learning in general. But now there are at least a few dozen of papers, right? And in these few dozen of papers, there have been some very successful attempts to create synthetic data sets for computer vision problems where creating data sets may be theoretically possible, but practically is, pardon the pun, completely impractical. So again, the prototypical example here would be the SunCG dataset. That's one of the most famous synthetic datasets at this point. And this dataset is basically about indoor navigation, about indoor scenes, right? About interiors of houses. So in this dataset, there are about 45,000 houses, in total about 50,000 floors, if I remember correctly, and there are some hundreds of thousands of rooms on these floors, right? And they were actually all produced by hand by placing some standard furniture models in virtual rooms and producing the houses. There are some relatively convenient tools for doing this that, for example, people in real estate use, and you can also use them to produce a synthetic data set like this. So what is now the benefit? What is the difference? What is it that you can do with this data set that you cannot get with real pictures? Because of course you can set up a room and of course you can take photos of the room, right? So the difference is that you know the 3D thing, right? That you know the 3D contents of your room. And the prototypical problem that they are solving with this, and the problem that was actually being solved in the original paper of Song, which presented the SunCG dataset, the prototypical problem was scene completion. Okay, so for example, suppose that I'm looking at you, actually even better, you're looking at me, and you're looking at a scene, right? So in this scene, you see different objects, and for example, the object detection problem would be to, given an image of me standing here, draw bounding boxes around me, around the monitor, around the speakers, and just label each and every object. The segmentation problem would be to draw accurate silhouettes, to actually understand what every pixel belongs to. But that is not all, right? When we are looking at a scene, we also understand the 3D contents, right? We understand what is in front of what, and we understand, distance to things, and well, there are some more conclusions that we can draw beyond just drawing silhouettes, right? And conclusions that we draw subconsciously. So the next level would be to actually, for example, learn to produce a depth map for the image, right? To learn to produce, and this is here, to learn to estimate which pixel in the image is at what distance from you, from the viewer, from the camera. But that is not all, because even, for example, for computer vision, you can say, okay, I'm a human being, I'm not working with a still image, my head moves a little, I'm working with a sequence of images that have slightly different viewpoints, and I have two eyes, so I have binocular vision, and therefore I have all of this information which actually can be combined to give me a relatively accurate depth map from the stereoscopic view, right? So there is a geometric argument that actually you can do more as a human being than you would be able to do from a still image, right? And it makes sense. But we actually do even more, right? We actually understand even more than just a depth map. So what we actually do is we, again, subconsciously complete the scene that we see, right? So we complete, we only see one side of things, right? And even with all the binocular vision, with everything, we only see, say, half of the surface of every object, and we reconstruct, we finish what we don't see from our priors, right? So we have some very well-learned priors about what a human being is, what a speaker looks like, what is, I don't know, what do we have here? So for example, by looking at this speaker, you can actually imagine how it looks from behind, maybe you cannot imagine what are the different outlets there, but you can reconstruct the shape, and you can basically see what the shape is, and you can kind of subconsciously see an object from all sides just because you know what this object should look like. And that's hard for a computer, right? So unless you have this very strong priors, it's very hard. And the original paper about the SunCG dataset was actually about trying to reconstruct the 3D models of all objects to complete the scene from just one depth map, right? So suppose that you have solved the depth estimation problem, but you only see the front of the object, so now you want to reconstruct and complete it. And that's, again, a problem that you can, a problem for which it is very hard to get real data. And just to illustrate what the difference is, here is the Metroport 3D dataset, which is actually also a very famous dataset. It is one of the best and largest datasets of a similar kind, the indoor scene dataset, which is actually real, right? So the Metroport is actually kind of cameras that can do panoramic views, and they installed the cameras, they moved it around some buildings, and they actually produced a very large, very interesting data set that contains panoramic views with labeled depth, with semantic segmentation applied to them. So they did a lot of work to do this. And they could cover 90 buildings. Okay, so previously we had like 45,000 in the synthetic data set and 90 in the Metroport 3D. And it's still very useful. Okay, so and by now, plenty of data sets begin to appear that use different kinds of synthetic, synthetic generators to actually to produce data sets for different tasks. And of course, there are synthetic data sets for self-driving cars and just for outdoor scene understanding. And again, they usually come from, datasets like this usually come from game engines, from the Unreal engine, from the Unity engine. They usually, basically, I even saw some papers that actually used the GTA engine to extract the scenes from the Grand Theft Auto games. But usually they do it separately because they do need to deconstruct and to get some additional information beyond the picture, right? Humans also. So again, of course you can get lots of pictures of humans, and of course you can get lots of, you can even get lots of humans to do things that you want them to do, provided it's not too hard. But again, the labeling problem, right? So if you want to do, for example, pose estimation or again depth estimation for humans, you have to have at least some kind of labeling, right? You have to take all of these pictures. Do you have a real picture? No, this is not real. You have to take a picture, and you have to actually manually label where the humans are and what is in front of what, and where is the arm, where is the leg, and that's very hard. So there is a recent paper about synthetic humans for real tasks, which shows again successful domain adaptation from synthetic humans to real humans. And the next step, of course, would be to produce not just data sets, right? So not just a collection of pictures together with depth maps, segmentation, viewpoints, etc., but to actually produce synthetic 3D environments, right? Synthetic 3D environments where you would be able to do things and see how the environment responds. Well, at the very least, you can move around the synthetic rooms, right? So there are projects like this. There is the Minus project, which uses the SunCG dataset and which allows you to navigate around the rooms. So you can basically send in a command like move forward a little bit, and it will move forward a little bit, etc. There is the House 3D simulator, which is produced by Facebook for the same purpose, and also a very recent paper. They basically do it to they also implemented a simulator for navigation inside 3D scenes of the SunCG dataset. And what is the main purpose of this? Why would you need navigation like this? Why is it not enough to do just still images? What kind of learning do you expect to see on the next slide? Right. So why would you need a simulator like this? You would need it to learn by reinforcement learning, right? So reinforcement learning is, I hope, how many people know what reinforcement learning is? Great. Okay. So we will not go into too many details on this. So basically, to train an agent by reinforcement learning, you need the agent to be able to do things, to do actions in the environment and see the environment respond, right? And that's exactly what the simulators are designed to do. So for example, the house 3D navigator was actually done to do room navigation, right? So you can actually navigate from one part of the house to the other. And this has obvious practical implications. Now you can take a robot and you can ask it to go to a specific room, and it will go to a specific room. Another very interesting work in the same vein, I just wanted to mention that it's not constrained to just navigation. It can be used in interesting ways. A very interesting work, very recent also, uses House 3D for embodied question answering. So suppose you have a robot inside that's not sure how many people can see it, but over here on the top right. There is a robot inside the virtual house, and you ask the robot, what color is the car? Okay, and it's not too hard at the present stage of question answering to understand that it is a question about cars and colors, etc. But the problem is the robot does not see the car, right? The car is somewhere around the house, and the robot first has to navigate to the place where the car is, and maybe learn where the car is, and then actually see the color and extract the color of the car. And this is very interesting, and this is a completely new application that I think would be impossible without synthetic data sets. And it's very interesting to see that it's starting to work, right? And they have some further improvements to the reinforcement learning side of things. I will not spend too much time on that. And we can do even more. We can do even more with the natural language processing side. For example, there is a very interesting work, also very recent, that uses the real dataset so far. It uses Matplotlib 3D, but maybe with SunCG we can do it even better. A very interesting work that actually learns to understand navigation instructions. Again, I'm not sure how many of you can read this, but it's a very long list of very detailed instructions on how to behave. Like, pass the pool and go indoors using double glass doors, pass the large table with chairs, turn left and wait by the wine bottles that have grapes by them. Okay? Walk straight through the room and exit out the door on the left, keep going past the large table and turn left. Walk down the hallway and stop when you reach the 2 entryways. And it is actually wonderful, and I would never, until the very last years, assume that deep learning models can actually understand text like this and can transfer them into actionable instructions for an agent in a 3D environment. But that's what's happening, right? So that's where we're going now. Okay, so how did we use synthetic data? What was how did we come around this problem? For us, for Neuromation, we actually began our work with a project where, it was a very practical, very industrial project of recognizing objects on supermarket shelves, right? So you go around the supermarket, and there is, there is a huge number of people who go around supermarkets just checking that everything is in order on the shelves. And people should not do this, right? It really should be automated. It's really beneath our human dignity to do works like this. So we wanted to automate the task of checking if everything is in order, and to automate this, you need to basically just do object detection on the shelves, right? So you need to understand where each and every Pepsi bottle is in the supermarket. And again, this is very straightforward, right? This is straightforward computer vision, straightforward object detection, but the data problem rears its ugly head here. So here, again, you can collect some photographs, but the problem is there are just too many objects, too many classes. Retail catalog has hundreds of thousands of different objects, and labeling a scene, again, takes a lot of work. So imagine the picture, you have a picture of here, imagine the picture of a supermarket shelf, and imagine how much work it is to manually draw the rectangles around every object, even if you have some suggestions from a model, still to actually check and put the labels on every object, it's impossible. So what we did, we generated 3D models of the objects. We rendered scenes, so these are synthetic images actually. We rendered scenes of shelves with the objects, and we actually did the recognition. Right. Another project that we are trying to launch currently is a collaboration with MonBaby, where we use baby monitors to, where MonBaby is a company that develops baby monitors, and for the baby monitors, they actually, their current solution is a button that you attach to the clothes of an infant, and it detects, it detects breathing, it detects heart rate, something like this. But of course it cannot detect the pose, and the pose is very important because sometimes babies break their arms in their sleep, sometimes they fall out of their cribs, things like this. So we would like to, so our joint solution would be to add a smart camera that watches over the baby. But then, of course, there is this problem of collecting the data set of babies breaking their arms, and to collect the data set of babies breaking their arms, you really, really need synthetic babies. You really don't want to go the real data way here. And the second interesting problem that I wanted to ask in this talk, and that people are trying to answer right now, is can we apply synthetic data to things like medical imaging? So I explained how synthetic data works for 3D environments, for indoor rooms, for things like this. But this is the easy part, right? So we know what a chair looks like. We can produce the 3D model of a chair. But how do we produce the 3D model of a carcinoma? How do we produce the 3D model of a brain tumor? The whole point of learning is to learn what they might look like. So it appears impossible, right? It appears impossible because if we knew what the brain tumors look like so well that we could produce synthetic brain tumors, we could probably just put this knowledge in the model somehow. It would be difficult as well, but probably we could. So the whole point of the learning is to understand what the brain tumor looks like. But actually, we can do things like this. And this is a field that is only now starting to take off, but there are already a few very interesting works in this field. And of course, the basic idea is, of course, again, that there are just a few buzzwords that everybody keeps telling in every talk. So I already mentioned reinforcement learning. Now, of course, it's time for GANs, right? So here the buzzword is GANs, the generative models that can actually that can actually produce new data items, right? And again, the same question, the same kind of skepticism is still in order. So how do I train again to produce brain tumors? If I trained again to produce brain tumors, why do I need a model, right? So the discriminator would be the model I need. And that was actually my initial skepticism for this whole field, but it turns out in some cases it works very well. And I will just highlight one specific case where there has been a very recent interesting paper that specifically used GANs. This is the problem of gaze estimation. Okay, not medical imaging, but actually pretty close. Gaze estimation is given a picture of a human face, find out where the human is looking, right? And so basically the target variable is the angle where the eye is looking, right, the angle. And this is, of course, of huge importance for mobile applications, for, I don't know, if your smartphone could actually understand which part of the screen you're looking at, it would open up lots of interesting possibilities. So for a long time, the state of the art was just take the faces and train a convolutional network and predict the gaze, right? Predict the angle. So this is a paper from 2015 where they added some tricks from standard computer vision, classical CV, and added a convolutional network, and it worked somehow. It worked. This was the state of the art. And then, that's why I'm showing this, in 2016, there was a paper that applied synthetic data to gaze estimation. And actually, the whole paper, I encourage you to look at it, it's very interesting. The whole paper is devoted to how well they made the 3D model. Okay, there is no machine learning in the paper. I mean, there is some, but 80% of the paper is about how we added the eyelashes, how we did the shadows, how we did this and that and this. And it's all about the art of synthesizing eyes and understanding where the gaze is coming from. And then, what is the machine learning part? How do they solve gaze estimation? They produced 1 million or several million artificial eyes, artificial images with known gaze. And then the actual machine learning that they proposed was nearest neighbors. You take the picture of an eye. Okay, you find an eye, you crop out the actual eye. That's a machine learning problem still. But then you normalize this image, and you look for the nearest neighbor in the data set of artificial eyes. And with that, they solidly beat state of the art. So this was actually very wonderful. But there was even the next step there. And the next step came, again, very recently. It came from Apple. And this is a paper where they learned gaze estimation from synthetic images, from the same kind of synthetic images as here. They took the same data set, but they also used, again, to refine the images and make them more similar to real eyes. So they used a special kind of GAN architecture, and everybody has their own GAN architecture. So here, the point is to fool the discriminator into believing this is a real eye, while at the same time having some sort of, how they call it, self-regularization to make sure that this eye still is similar to this synthetic eye, right? So that we can reuse the target variable. So they look at the same, to the same point. And here are some numbers. That's the only number on my slides, but the 9.9, this is the error in the angle in degrees, so the smaller the better. And this 9.9 is actually the error that they made with unity eyes and nearest neighbors. Okay, and this solidly beat, as you can see, all previous attempts to learn complicated computer vision models. And Apple, with the GANs, could take it to 7.8. Okay, so I'm running out of time, so I'd like to conclude with whatever. So synthetic data is becoming ubiquitous on large conferences now, and actually now there is a typo here. It's not ICLR 2018, it's ICLR 2019. They again encourage you to look at this. The papers submitted to ICLR 2019 are already available at Open Review. And while there still might be mistakes in them, they have not been reviewed, you can already look at them, and you can see that there are quite a few synthetic datasets in there. There are quite a few interesting new datasets and interesting new directions for synthetic data. And I believe, and we at Neuromation believe, that this is the future in some way for computer vision, and maybe for different applications as well. We believe that there are things that you just cannot learn from real data, because we humans have some kind of deeply ingrained priors that we have learned over our whole lifetimes, and how are we going to emulate a human lifetime with a data set? I'm not sure. And the way to go would be to use synthetic data. So thank you, and I think I will finish with the slide of our wonderful team, and if you have any questions, I stand open for them. Thank you.
Sergey, thank you for your speech. Folks, do you have a question? Questions? Hello?
Hello.
Is it doing? Oh, okay. So I have a few questions. First of all, I want to thank you for your talk. First one is, I want to generate the human body data set with action sum. What would you recommend for software to do this task?
What would I recommend? What?
Software.
Software? Oh,
yeah.
Usually people use standard game engines, like Unity or Unreal. So whichever you like most. But, okay, my clicker doesn't work
Maybe
anymore.
something simpler.
Yeah, but
I mean, you should be a game developer to like use this Unity and all the stuff. Maybe there is something simpler that already use it in machine learning to generate that sets.
Yeah, specifically for people, I would recommend to look at the paper which I had somewhere here. Yeah, this one. This is real. Usually every paper, I mean, I cannot recall it off the top of my head, but usually every paper on synthetic data has a section where they describe in painful details how exactly they generated the data set, what were the libraries, etc., etc. So I just recommend you to go with the flow of how other people do it.
Okay, thank you. Another question is, there is generative models to generate data. For example, you have some data set and you train the GAN. It models the distribution of the data, and you just sample the images from this distribution. Should this be considered as like synthetic data in this sense? Is it used a lot, and is it a very good idea to do?
Yeah. Okay. So yeah, let me. Okay, I think this is actually an excellent question because it allows me to get to the slide that I did not have time to get to. So the answer is the following. Yes, you can train again, and you can try to generate just images from the synthetic distribution of the GAN. But it will not be very interesting, right? It will not be very interesting exactly because of the skepticism that I explained, that once you have already trained the GAN, why do you need to train anything on the result of the GAN? You already have your discriminator in there. So you can just take the discriminator and fine-tune it for your task, and you're done. There will be nothing new coming out of this GAN that the discriminator has not trained on already. But what people actually do and how it actually works, for example, in a very this is a paper from September this year, so not very recent, and how people actually do it, for example, in medical imaging, they train a GAN to produce synthetic images, for example, MRIs of brains, and then they use a conditional GAN architecture to add the target variable in some new way that has not been seen in the data. So, for example, here you add the tumor, and you have two different data sets, one with the tumors and one just generic MRI images, and you train the GAN to produce just generic MRI images, then you fine-tune it to make it into a GAN that produces tumors and produces MRIs of brains with tumors, but then you actually extract the tumor, well, not physically, but you segment your MRI, you find where the tumor is, and you learn a transformation that moves the tumor to a different place, right? That shrinks it, that grows it, that does something with it. So you basically use, for example, your unlabeled data to add variety, to learn the variety, and to add this variety to the small labeled data set that you have, for example. Okay.
Semi-supervised or something?
Kind of, yeah.
Two other questions, and that's all. Do augmentation use it for synthetic data sets?
Data augmentation, of course, you should always use data augmentation.
And another problem you didn't mention is the domain shift. It's a big problem, but in general, could you mention some like basic ideas that set you up that use it? Uses, for example, as I said, you have synthetic data set, you train new model, it's very good. You do it on test set with real data, it's a huge error between them. And what is the techniques just to Google that or something like that?
Well, actually, there is no silver bullet here. You have to solve this problem again and again for every new domain. So, but usually, yes, augmentation helps a lot. Yes, as we see in some applications, refinement like this helps a lot. But this is still not mainstream. There are just maybe 2 or 3 papers that do a pipeline like this. So I don't know what will work in your case. Nobody knows. That's what bleeding edge research means.
Hello, Sergey. Thank you for your talk. So my question is, how do you actually recommend to use synthetic data? So suppose I have lots of synthetic data that I already generated, like tons of it. So should I first pre-train the model on it and then do a transfer learning to my specific problem, or should I mix them with my actual training data? And if so, what is the ratio, 1 to 10, 1 to billion?
We are actually, right now we are in the process of producing a white paper that addresses these specific questions of what should be the ratio, etc. But yeah, the rule of the thumb is, of course, if you have a real training set, a real labeled data, even if it's a very small data set, it will help immensely. Right, so of course, training on a mixture of synthetic and real will always be much better than training on synthetic only. Okay, but hopefully the mixture of synthetic and real will be much better than real only as well. Right. So yes, of course you should mix in your real data if you have it, of course. And again, of course, I cannot give you a number like 100 to 1. No, I don't know the number. Oh, okay. Actually, we tried it both ways. Sometimes it comes out better one way, sometimes the other, as usual with machine learning. So I would just suggest to try it both ways. Yeah.
Hello, Sergey. Thanks for your talk. I was wondering whether you see potential in synthetic data for time series forecasting. Have you looked into prediction problems using synthetic data?
Yeah, thanks a lot. Again, this is the part where I did not have time to go. There are domains that are very well suitable for synthetic data, like computer vision, and then there are domains where we don't know yet how to apply synthetic data. And one of these domains would be, for example, natural language. So for natural language, you can try to learn some easy transformations, like, for example, the transformations that Mariana was talking about. For example, try to switch words for a synonym, try to reshuffle the syntactic tree a little bit, syntactic tree. But truly synthetic text generation is basically the problem of understanding text, right? So to generate the synthetic data set for natural language, you would actually first need to solve your problem, which doesn't really work. And as for time series, I think it's somewhere in the middle, right? So I think it would depend on the specific time series. We actually, at one point, we looked at trying to produce synthetic data for banking, for credit card fraud, for things like this. And this is exactly transactional time series data. And our conclusion was that, yes, it's possible, but it hasn't been done yet, and it's still a subject of further research. So the answer is, I would try. I'm ready to try, but there is no answer yet.
Great, that's all. Applause for Sergey. Thank you.